I'm Carl. I'm a lecturer in computer science. I work mainly in AI, large language models. Large language models, visual language models, and also visual language action models moving into this space. So for 20 years, I've been building robots in my bedroom. And 20 years later, I am still building robots in my bedroom. The technology has changed massively, right? It used to take forever to handle and craft robots. Now, using AI, we can produce them in a few weeks. We have our work which has just been set up here. It was produced in a few weeks. Again, just using ready-made materials around my bedroom. And that's how I started. So the first robot I made was made of this Xbox Kinect. It was kind of a mismatch of just things like electronic components I could take out of things and use. As a child, I would drive my parents insane by taking things apart and not being able to come back together again. But that inquisitive nature, right, carrying that on into adulthood, and still doing it today is just something fascinating. But there's a reason for it. It all sounds good, it's all fun, but there's a serious reason for doing this. And that is that the systems that I was working on at the time, conversational AI systems, moved beyond simple rule-based systems really quickly. But the robots didn't catch up to that. A lot of the robots at that time, the commercial robots, couldn't run these systems. So I started building my own robots to be able to run these systems. And now, not much has changed. My PhD students now, I build robots for them because they're working on systems that cannot be applied easily on standard commercial robots. Okay? So, let's say, unfortunately, I don't have slides, so I'm kind of going through memory of what these slides are. So, last year, I contributed on 2 reports for the UK Government Office of Science on humanoid robots and AI-driven robots. And basically, what we're trying to do with those reports is see which domains robots could be used in. Okay, and social robots could be used in. And believe it or not, entertainment was kind of the easiest. Which you can think, yeah, entertainment, but healthcare and education are also the most complex, and they're most complex to deal with in real-world scenarios. So, kind of trying to get there and trying to understand it, it's kind of baby steps, right? And this is the difference between academia and industry. When it comes to stuff like this, in academia, we have a bit of a free rein. We can test stuff, we can do stuff. We don't have to answer it. We have to answer ethics, but we're pretty cool to be able to test all this stuff out. In industry, there's a different kind of setting, isn't there? Like, there has to be some kind of rules here. So, one of the cool things that we do is we just test this really kind of advanced systems that students are creating. And it's what we're starting to see is students thinking, instead of buying a robot or using an existing robot to create a research project around, we can start building robots to answer research questions. And in this, we get more novel research, we get more interesting questions after the students. But also, we're advancing quicker than ever, and for students to be able to be on the brink of that and think outside the box is really important. So I'm going to start talking about the 4 projects now that I want to talk about. So the first project was, as previously mentioned, my work in robotic lift synchronization. So again, I had to build a robot to test this machine learning algorithm out. Basically, the machine learning algorithm extracted visemes from phonemes. Visemes are your lip positions, your smiles, your frowns, and matching them up to phonemes in real time required training a machine learning algorithm to detect and process this in real time. This was not an embedded layer in the NLP system. It was actually a pre-processing thing, like a pre- and processing thing in real time. So the idea was that you wouldn't have to just have a single robot voice. You could train it on any robot voices, well, roughly anyway, and it'd hopefully improve over time. So that was one of the first examples, actually, of a machine learning algorithm to do this and to use this with. That's from project 1. Project 2 was what I did in my postdoc. So this is more kind of in the conversational AI field. So we're talking about sort of 6 or 7 years ago now, when I was doing my postdoc. And large language models were just kind of coming out, so lots of like Gardner at the time has been a big language model that everyone was using, and with GPT-1 territory. And I created a robot. So this is Moira, but I actually wanted a robot, an older male-looking robot called Euclid. And what I did is I wanted to train an AI system to help people in cooking scenarios. Okay. So I trained a common sense knowledge database. And what I did is I got students to perform recipes over and over again, and created this common sense knowledge database. And then what I did is I took all the embeddings out of it and just used the common sense database. So what happened is you could do a cooking task and make a mistake, do something wrong. And you could say to the robot, oh, the pan's burning, what do I do? And the robot will tell you what to do. You could use this common sense knowledge database and generate from that. And that's really important, because when we're using real world robots in real world scenarios, we need this common sense knowledge. Common sense knowledge is really hard to encode in AI. Generally, AI lacks common sense, because common sense isn't directly embedded, it underlies everything. Okay? And using this external data set, which was unstructured, by the way, you could kind of get this rough structure of an output, and it would say, oh, well, I think this has gone wrong. I think we should do this. Okay. So now, and then the next project I want to talk about is a student project. So my PhD student, Byoku, she is working on Euclid, which is the other robot, and she's working on creating a conversational AI system that is completely configurable in real time to different scenarios. So we can put the robot in a school, and we expect that robot to behave in a certain way. So using the Big Five personality types and Gardner's multiple intelligence theory, which are all divided into subcategories, you can imagine each of these subcategories as having sliders on them, reconfigurable in real time. So her project is about being able to put a robot in a school, for example, or a hospital, and you want that robot to act a certain way. We don't want to retrain that robot each time. We don't want to create a robot that's just for schools, or a robot that's just for hospitals. Okay? So it automatically refigures using prompts. And you can imagine all these sliders start to change, and you can manually adjust these settings. Automatically adjust these settings so the robot can work in that situation really well. And finally, I'm going to talk about Lewis's projects on this robot, which hopefully we'll be able to demonstrate soon. It looks like it's going to live as I'm talking. So one of the fascinating things we can do with this robot is we are working on an advanced LLM system. So with Moira, what we can say is we can do a prompt and say, what can you see? And Moira will look around the room and she'll be able to describe to you exactly what she sees, down to the clothes you're wearing, down to the facial expressions you have. Okay? And then if we come in an hour's time, for example, and say, what do you see now? She'll look around the room and she could tell you what is different about it. Maybe people are not as happy, maybe people are left. Also, she can also make predictions into the future. You can say to her, what do you think will happen next? Now, she knows, because all this is feeding back to an LLM, that chances are furniture may move, but walls probably don't. People are probably going to lightly move around, but the floor's not going to move anywhere. So these are the kind of spatial and these spatial reasoning that we're embedding into this system for the robot to be able to detect these changes. And this is really important, and this is kind of where we are at the moment with this robot, because we want to be able to start putting her in scenarios where there's real dynamic environments. The conversations are going to be changing. Things are going to be adapting all the time, and she's going to have to adapt with it. So yes. And finally, one of the next things I'm working on, again, sorry I don't have the slides. I have a USB stick, but I don't think I use my computers. Science going to VLAs. So I'm sure we all are aware of what VLAs are. If not, I can recap. So we have large language models. Then we have vision language models, which is what is on here. So not just a large language model like ChatGPT, but it's knowledge-based. But we have a computer vision system. So we have visual language. And now we're moving into visual language action models. Okay, getting robots to be able to think, see, and do a task. So usually I have my glasses on because I have the Meta glasses, and my wife is pleased because I've never done so much housework in my life, having to record myself doing the pots and doing all these things to get into data. And then what I'm doing is I've created a robot, a version of this with arms. They can do very minor tasks in certain ways. But that's what we're trying to do. We're trying to get this idea of, if we keep doing the same tasks over and over again in different ways, what are the kind of thresholds between these tasks where we can gain more knowledge? So yeah, that's another project we are doing at the moment. So, are we about ready, Lewis, or are we still?
Yeah, just 1 second.
She also detects movement as well, so speaker's not on. So the other thing that she can also do is she can also detect people in a room and track you around the room and direct conversation to people as well, so she knows who she's talking. Okay.
Yeah, should be.
Okay. So let's do the.
Introduce yourself.
She may be a little slow because she runs completely offline.
Hi, I'm Moira. I'm here at the European Chatbot and Conversational AI Summit with my human colleagues from the HRI lab in Edinburgh. We're all about building robots ourselves using accessible parts and 3D printing, rather than just buying them off the shelf. It's pretty fun to get your hands dirty while making something talk back to you.
So yes, but one of the really cool things you can see about this is she's dirt cheap to make. It's about £700 to build this robot. When you compare to other commercial robots, it's about £3,000 in similar types. So that's really cool and really fair at the same time. So let's do this next trick. Okay, I don't know how this is going to work. What do you see?
It looks like we've got quite an audience here. Lots of people holding up their phones, probably recording the talk or taking notes on what's being said. The vibe is pretty standard conference energy, focused but with that modern twist where everyone wants to capture it digitally too.
Okay, so you can see that it's pretty good, it's pretty accurate. We're building more into it all the time. The most impressive thing about the system isn't just the system, it's the fact that Lewis, my PhD student, has learned to run on a standard, cheaper university laptop. It's not on any cloud software, it's running completely offline on an 8 gigabit RAM memory laptop. It's the cheapest the university gives you. Everything we do, we try to get the best out of. You know, we do a lot of parallel processing across CPU and GPU to get the best out of everything we can do. The reason for that is because if we start wanting to put robots into actual scenarios, the restriction's always been around cloud software, right? And the robots we have are always a nightmare to set up because you put it there, you take it to a conference or somewhere, you put it on, you try and connect it to the Wi-Fi, it doesn't connect, and you spend the rest of the time just messing around with that. That's always what happens. So with this, it runs completely offline. So we have a cheap robot running on a cheap laptop. And that's what we're about, okay? And so I'm from Edinburgh University, not Edinburgh University, but Deep University. We have to kind of work with what we've got. And I really believe that necessity is the mother of invention. The less you have, the more you can do. And it forces you, pushes you to think in different and new directions. And yeah, this is what Mara is about. So I know time is kind of ticking, but hopefully if we can set her up somewhere, we will, and you can have a chat with her, if that's okay. Otherwise, I will pass back over to you and we'll take things up later.